In this video, we're going to look at how we can design a reinforced concrete beam for shear using S-line. Now, for a bit of background on this problem that we're going to use, we're going to have a 10-meter long simply supported beam. And this beam will have a cross-section that is 750 millimeters deep and 400 millimeters wide. It's a rectangular reinforced concrete cross-section. You can see a preview of it on the right-hand side. In terms of reinforcement, for the flexural bars, we have 6 20M longitudinal bars, although we're not really concerning ourselves with the flexural rebar design. And for shear reinforcement, we have 10M ties. We're going to assume that we have 40 millimeters of concrete cover over our steel, and our concrete strength is 30 MPa, and our steel yield strength is 400 MPa. As far as loading goes, we're going to have a dead load that is a uniformly distributed load of 35 kilonewtons per meter, a live load of 30 kilonewtons per meter, and we're going to factor those into a load combination that will equal a total of 88.8 kilonewtons per meter. And we want to determine the required stirrup spacing to meet our demands. And while doing this, we're going to use the simplified shear design method described in the CSA 2014 design code. And we're going to start by looking at S-line, how this can be set up in S-line, and then we're going to compare to hand calculations. And just to describe the steel shear resistance a little bit more, we're going to make some assumptions right off the bat. We're going to assume that we have two different sets of stirrup spacing. So we have a 10-meter long beam, and we're going to say that in the first 1.5 meters away from the support, we have a different stirrup spacing than we do in the interior. So we're going to design those two separately. So this will be the 1.5 meters away from the support, which will have a higher shear demand based off of the shear diagram that we see here. And the interior 7-meter beam length is going to have a lower shear demand, so we'll have different stirrup spacing to meet those demands. I'm going to go into S-line now, and I've already set up the geometry in this model to meet what my requirements are. I have a 10-meter long beam, 10,000 millimeters. You can see my loads, 35 kilonewtons per meter for my dead load. My live load is 30 kilonewtons per meter. And I also have the factored load combination of 88.8 kilonewtons per meter. And right now, I'm using the default stirrup spacing that I will need to adjust further. So you can see here that it's giving me different stirrup spacings at different regions within my beam. But I'm going to simplify this down into just two different regions, one set on each side of the beam and one in the middle. So I can go to the Edit menu and then go to Member Reinforcing. And within the member reinforcing here, I can see how this will be laid out. And we're not going to adjust this just yet, but we can see here that we have 6 20M bars. And if I scroll down here, you can see that we have our stirrup definitions. So we have stirrups on the left end, the middle portion, and the right end. And you can see on the left end, we have 2 sets of stirrups that we can specify. Right now we have 8 stirrups on the set number 1 at 275 millimeter spacing, and then 5 at 350 millimeter spacing. And the same thing mirrored on the right hand for set 4 and 5. And for set number 3, we have a larger 475 millimeter spacing, just filling in the area in between those two zones. I'm going to go ahead and run an analysis and code check, and I'll just click Analyze Code Check. And we get our results. And if I just look at the bottom of the screen here, we can see that we have a shear utilization of 1.17, indicating that I'm about 17% over my capacity in terms of my demands. And my positive moment utilization is well in exceedance of my capacity. I'm not going to worry about that one though. I'm just going to focus on shear utilization. I can look at the shear results if I want to look at results, menu, and then shear diagrams. Here I can see the results for my shear. And you can see this blue line indicates my shear capacity envelope. So it's looking at the shear capacity at different locations along the length of my beam. Every change in slope is related to a change in the number of stirrup spacing or change in our stirrup spacing. And I can scroll my mouse through this graph here and see what the values for the capacity and the demands are for this particular load combination. And you can see at the very ends, we're exceeding those capacities. We have about 383 kilonewtons of shear, but our demands or our capacities are less than that, 329. So obviously something needs to change. We can also go to the results report. And here I can look at the shear and torsion section by just clicking on this link. And it's going to show me here where my utilization is highest. 10,000 millimeters is the end of my beam for load combination number 8, which is my factored load combination. And it's showing me my factored shear force and my shear capacity. As well, I can see my steel and concrete contributions to the shear capacity. Now I've gone ahead and I've calculated what sort of reinforcement will be required to meet these demands. Now this is obviously something that would require an iterative process, which S-line is great for, but to make this video a little bit more succinct, I'm just going to enter those reinforcement requirements. So I'll go to the Edit menu, Member Reinforcing, and I know here that I'm just going to break this up into basically 3 different sets of stirrups. So I'm going to ignore stirrup set number 2 and number 4. And all of our stirrups will be in either set number 1, 3, or 5. And I'm going to use 200 millimeter spacing because that's what I calculated will meet my demands. And we'll go over the calculations in just a minute. So I have 8 200 millimeter stirrups rather. And here we can see that that will take up 1600 millimeters, which is about the same as the length of that zone we were talking about earlier. I'll go 200 millimeters on the right side as well. And in between, we're going to set this to be 375 millimeters. I'll then press OK. You can see that this diagram has updated, showing me the reinforcement, the number of bars, or stirrups, sorry, that I need at the indicated spacing. I can then go to the Run, Analysis, and Code Check dialog again. Run my code check. It's going to regenerate all my diagrams for me, and click OK. And what I want to direct your attention to is this green light here. This is indicating here that my shear utilization is now less than 1, meaning my demands do not exceed my capacity. I can look at the results, and I can go to the shear diagrams now. And in the shear diagrams tool, we can see that this pink line indicating our demands is well within this blue envelope for my capacity. And I can scroll my mouse through this line here, and I can see here that the maximum capacity that I have in my beam for shear is 460 kilonewtons. And in the middle, where I have the 375 millimeter bar spacing, I have a maximum capacity of 319.5 kilonewtons. And I'm going to go and check to see if those match my hand calculations. We can also go to the results report and just look at the updated results here. So I can see the shear and torsion section is showing me that my factored shear force is 383 kilonewtons, and my demand, or my capacity rather, is 400.6 kilonewtons at x equals 10,000 millimeters. So right at the end, where I have a slightly lower capacity than my max. And we can also see the contributions from steel and concrete. So let's go into my PowerPoint slides now, and I'm just going to describe the process for how we calculate those by hand. First of all, we need to make sure that we understand that the beam shear resistance is equal to the shear capacity of the concrete plus the shear capacity of the steel. And we also need to determine the effective shear depth, which is found using these formulas. So it will be the maximum of either 0.9 times our effective depth or 0.72 times the height of our beam. And the maximum is 620 millimeters. So that's going to be the number that we use in the future calculations. Now we know our maximum shear force. We've seen that already within S-line. But just to calculate this, we have 88.8 kilonewtons per meter as our maximum load applied to this beam that's 10 meters long. So the maximum shear force would be 443.75 kilonewtons. However, our design shear force will be found at a distance of dV from our support, and dV, as we just found out, is equal to 620 millimeters. So the design shear force will equal 389 kilonewtons. And we want to make sure that our shear capacity exceeds our design shear force. Now let's look at the concrete contribution to the shear resistance. We can use the following formula to calculate this resistance. And based on all this information, we find that we get 159 kilonewtons of concrete shear resistance. I'm just rounding up there for simplicity. And if we look at the steel shear resistance, well, we have to look at this in two different parts. We have to look at the end portions where we have different stirrup spacing than the middle. So for the end portions, these ones right here, just to remind ourselves that we have our design shear force of 389 kilonewtons. So we have to have more capacity when we combine the concrete and steel shear capacities than our design shear force. So we can use this formula to calculate our shear steel capacity. And knowing that we have a spacing of 200 millimeters for our stirrups, which I referred to earlier within the previous S-line demonstration, we can calculate that our shear contribution to the shear capacity, or steel contribution to our shear capacity, is 301 kilonewtons. And if we add our shear from steel and concrete, we find that our shear capacity equals 459 kilonewtons, which matches what we calculated with an S-line. Now, if we look at the interior portion of our beam, where we have slightly lower demands, 310 kilonewtons, that's this section right here. Again, we still need to make sure that our shear capacity exceeds this demand. So using the same formula as before, but a larger stirrup spacing of 375 millimeters, we can find that our steel contribution to the shear capacity would be 161 kilonewtons. And if we add that all together, our total shear capacity for this portion of the beam would be 319 kilonewtons, which exceeds the 310 kilonewtons of our design shear force for this section. And this also matches the value we got out of S-line. Now, obviously, it's great that we know how to do this by hand, but having the ability to iterate on this design process, which can often take several iterations, is definitely more efficient to do within S-line, where it allows for much more quick processing of the information without having to go through the calculations